Ugh. Electricity. Let's see. So lesson 10. We did work on power last time. Yeah, lesson 10. How's your chemistry going? Is that finished or nearly finished? Nearly finished. Okay. Okay, good. Right. So what we're looking at here, I think who was talking to me this week about an exam question that had that was you, yeah. So what did you notice in that question that was a new word? EMF, yeah. And that's what we're going to have a look at today. Yeah. Okay. Let's see. Oh yeah, sorry, you need to write this down. Electromotive force and internal resistance. What's going on?
It's fine.
Is it? Okay.
You know, I need that.
Why?
I'm too big.
Are you putting your feet on that?
Oh no.
Ah, okay. Alright, have you got that? Yep. Right. Okay. So I used this word already, kind of loosely. Potential difference. It means the same as what? Voltage, yeah. So just to be clear, I know I've said it a couple of times already, but to be really clear, potential difference is just another name for voltage. But with that said, what exactly do I mean when I say EMF, electromotive force? Electromotive force, EMF. Well, before I give you the meaning, let's try and think about what it could mean. So, electromotive. Okay, let's look at the start. Electro. What does electro mean here? Electricity. Okay. And motive? Motion. Yeah. So, electromotive force. Electrical, yeah? Yeah, the force that what? Yeah, the force that would make electricity move. So, in other words, kind of like the driving force nearly. What is it precisely? Precisely it is, it's the voltage by a source of electricity such as a battery, and it's generally defined as the electric potential for a source in a circuit. So a device, now before you write all this down, a device that supplies electrical energy is called the seat, and EMFs, is that the door? Okay. Now we have everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, anyways, well, how much do you need to write down? So, electromotive force is the voltage developed by a source of electrical energy, such as a battery. In other words, the simple way to put it is EMF is the voltage developed by the battery, the provided voltage to the circuit from the battery. It's not quite the same thing as voltage, although it's nearly the same thing, and the unit, of course, is the volt. So if you can write the first sentence down. Got that? Got that? Yeah? Okay. So, let's continue. You don't need to write all of the next part down. I'll just give you the key things you need, because just, keep it simple. Another definition for it is as the electrical potential So you can just write down also known as electrical potential. Yeah, also known as electrical potential. You can just add that. Got that? Yeah? What else can we say? And give me some examples of things that provide a voltage. So the battery in your phone is one. What else provides a voltage? Battery in a car, yeah. You know, the solar panel, the fan, the wind, yeah. All these things can be used to provide a voltage. They're all called the seat of the circuit. You don't really need to write that down. And EMFs convert chemical, mechanical and other forms of energy into electrical. So for a battery, it changes chemical into electrical energy. So it provides an EMF. For what Chu just said, the wind power changes wind into voltage. So that's the EMF there, and so on. Okay. So what exactly is the difference between EMF and potential difference? Well, really, not much of a difference, really. I generally say, for example, an EMF of 1 volt means each coulomb of charge is given 1 joule of energy, whereas a voltage of 1 volt between 2 points means each coulomb could do 1 joule of work. So the difference is very, very simple. EMF gives the joule per coulomb, and potential difference takes the joule per coulomb. So if I have a battery, I can say the EMF is 9 volts. If this goes into a light, I can then say the potential difference is 9 volts. But you can use the word voltage for both. But I think to be more precise, you should distinguish between the two. So battery is EMF and a resistor is potential difference, but both are voltage still. Okay. Right. Let's continue then. Okay. Now, just before I draw that, just to explain why we need to draw this. So I don't, or do I have a battery? Well, we all do.
Wow.
Yep.
Wow.
Battery. Now, you're making fun of this, but yesterday I managed to program this to check Lewis times. So I can check the Lewis on this. But what's so impressive about checking it on your phone? Of course you should be able to. Yeah. Anyways, battery. So, inside the battery, I need to turn my writing pad on. What? Are you making fun of my phone? You're just jealous. Yeah. You're jealous I have Mr. phone and you don't. Okay. That's okay. Maybe one day you'll be cool. Alright, continue it. There we go. So, let me just draw a battery that you'll all recognize, like an AA battery, something like that. So these are normally 1.5 volts. So we say the EMF is 1.5 volts. And in our mind, because it's a battery, it actually has many cells. So there maybe is a cell here, and here, and here, something like this. And that's wrong, because this side is the positive, this is the negative, so it actually should be that way. And that's there. And then this connects to the end. But what happens is, in real life, it's like there's a small resistor inside it. Now, it's important to really emphasize like. There's not really a small resistor inside it, because if there was a small resistor inside it, that would be stupid, because you're wasting energy by heating this resistor up. We're just saying that it's the model that we have in our head is that we have a perfect cell and a small resistor. But there's not really a small resistor, it's just our model. So this is the EMF, and this is the internal resistance. Okay, so that was the name of the lesson. EMF and internal resistance. Now I think it would be a good idea if you draw this. Yes, Sean?
Yes. Teacher,
Yes.
how much sugar do you really add in your coffee?
I don't put any sugar in my coffee.
Really?
Yeah.
You look well.
Just pure coffee.
You're bitter? It's so bitter.
I can handle it.
Sweet sugar in it.
3 sugars?
Yeah. It's still so bitter.
You're just a boy.
Yes, boy.
This is why.
I'm fine. Right. Mr. Right.
Okay, did you draw that? Yeah. So we would like the internal resistance to be small. In fact, this is why your battery in your phone or your computer or whatever gets warm, because the internal resistor the work it does, it warms up. Okay, so a warm battery is bad because it means energy is being wasted. Yes, KJ?
Why do you put it on resistance?
No, I didn't. You see,
No,
I said it's like.
It's like.
It's not really in there. Do you know what I mean? Like, this is just our model, our picture. A simple picture that represents life for the battery. It's not really like this, of course, because if it was really like this, you would just take this out. But you can't, because it's not exactly like this. But for us, it's enough to imagine it's like this. It's an approximation. Yeah, essentially it's just there to say that there is resistance in the battery. How that resistance is there is beyond what we do, because, you know, it's complicated. It depends on what type of battery it is, the materials, the chemicals. So as you put it, it's just there because there is internal resistance and we just imagine it like this, but of course it's much more complicated than that. Yeah. Right, so continuing. So this circuit is going to be quite useful. Before you draw it, let me just explain what it is. We have our battery here, our cell here, and across it we put a voltmeter, and then this powers a variable resistor, and we can measure the current and the voltage, and we can change the resistor here, so we can increase or decrease it. And in a moment we'll see why this circuit is useful. So if you can just draw this now, please. Got that? Do we have the same shoes? No. We have similar shoes.
Mine is similar.
minor sketchers. Okay. Got that drawn? No? What?
So beautiful.
Show me.
What?
Show me.
We don't have to do that.
That is beautiful.
Yeah.
Yeah.
How?
Admit that.
Yeah. Admit it. Yeah, admit it. Admit it, Monica, it's beautiful.
Don't laugh.
She doesn't understand. Okay. So, Jerry, I'll make you useful for a moment. What I want you to do, you know Kirchhoff's rules? I want you to use Kirchhoff's rules starting here, and we go around. Okay, so this is EMF. So EMF minus, what will we say? Well, maybe I should. IR, very good. And then here, minus IR as well. Little r, and this one we'll call it big R, okay? And we'll call this E. So by using Kirchhoff, we can make this one, EMF minus, now you said IR, that's fine. But actually, you know the V here, because you have a voltmeter. So you can actually just say minus V. And you know the I, because you have an ammeter, so you can say IR. So this is from Kirchhoff's loop rule. We can rewrite that as this, or like this. So we actually have two ways to write EMF. I'll just write them down here. We can say EMF equals V plus IR, and this is from the voltmeter, and this is from the ammeter. Or, as Jerry said, if you knew the or and you didn't know the voltage, you could write it like this: I or plus or. So you have two formulas, this one and this one, for EMF. But really, they're not new formulas, because you can find them just by using Kirchhoff's rule. So, they're formulas, but they're not really new formulas, because we get them from just using Kirchhoff's rule. So there's nothing special here. Got that? Yeah, continue. Continue. Now, I suppose, yeah, there's actually a couple of ways to think about this. So, okay, let's actually have a look at this here. If I was to take this formula, what is the thing that we change and what is the thing that we measure? Yeah, we could change the big R, although this formula doesn't have big R in it. Yeah, we're changing the voltage and then we see a change in the current. So if we were to make a graph, what should we put on the X and what should we put on the Y? No, the X is the V, because we just said we're changing the V. And then we see a change in... No, we change the V. We change the OR, which causes the V to change. In this formula, there is no OR. By changing the OR, we change the V in this formula. And then we see a change in the I. So this here is... This is Y. So I should change it in this form. I or equals EMF minus V. So then I can get I equals EMF over or minus 1 over R V, or in other words, I equals minus 1 over R V plus E over R. And I'll make the graph. Now if you look at this graph, this is Y, this is X. So what is this like? M, and this is C. Is it going up or going down, this graph? This graph of I against V? Going down. And in fact, the slope here is what? Minus 1 over R. So you can say R equals minus 1 over M. Now that's important, because I said it's not possible to take this out. It's not possible to measure it. But by changing the V and measuring the change in the I, and by using this rule and making this graph, we can actually figure out how big the internal resistance is. We can work it out. And that's quite useful, because we would like to know what the internal resistance is. Now you might say, can we know the EMF? Yeah, we can know the EMF, but there was two easy ways to know the EMF. We could have just looked at the battery, because it says it on the battery, so that's one easy way to work it out. And secondly, another way to work out the EMF is just to take the battery and just stick a voltmeter on it. And we already had a voltmeter, so we don't usually care about knowing this, because we already know it, the E. It's this part we care about knowing. Okay? In the exam, I think what they like to do is they like to give you data for V and I, and then ask you what is the R, and to make the graph. So you need to remember that the I goes here, the V goes here, and the slope is useful like this. Okay? So I would like you to write this, which side down? This side here. So first write this down, then write this, then this, and then write this, please. Yeah. Got that? Yeah? Not yet. Got that? Sean?
No.
Okay. Got that? Bruce? Bruce? Not yet? Say again? No. That's square. Yeah, we haven't done that formula. In fact, well, no, actually, we did something like it when we did power, didn't we? I squared R. Yeah, but you're saying I squared R T.
Yeah.
T for time. Yeah, this is how much energy comes from the resistor.
Yeah.
We haven't really done that, but you have this formula, P equals I squared R,
Yeah.
and P is
Oh.
work over time. So work is I squared R T. So we kind of did it. Okay, continue. Yep, alright. Yeah. Now you see, there's other ways to do this too, but I don't like this way, but I better show it to you because I think I've seen it in the exam. So if you were to rewrite it this way, here V equals or I minus E. If you were to write it this way and put V here and I here, then this would be the slope, and what shape would you get? It'd be upwards here. But I don't really like this way because the voltage is really what you're changing when you change the big R, you know. But just so you know, in the exam, I think I've seen them do the graph both ways. If they don't say what to do, you have your choice. In both cases, this is the formula that helps you work out what you need to do. Yeah? But I don't really like this one. By the way, when we did our IV graphs, what did we have on the Y and what did we have on the X? Yeah, because the V is the one that we changed. Yeah. Anyways, we won't worry too much about that. My point is the same. We can calculate it. Okay, so let's have a look at this question. We set up a circuit. Oh, some vocabulary. Terminal voltage means the voltage across the battery. Let me draw that for you. Here's my battery. And here's the resistor. And that's an OR. And let me just draw it again. I just want to make a point here. Okay, so if I put a voltmeter here, what will that tell me? The potential difference here. And if I make this R bigger, what will happen to this V? Bigger or smaller?
Smaller.
V equals I R. Make the R bigger. I think the V should be bigger. If we look at this, although we don't really know what's happening with the I. So anyway, if I do this, the same result or a different result? The same. Okay, what about if I do this? Same. What about if I do this? Okay, now lastly, what about if I do this? Now what about if I do this? No. Still the same. So my point I'm trying to make is, if I put the voltmeter here, or if I put the voltmeter here, although it looks different, it's actually the same. Because if I draw the current comes out here, starts at this one, ends at this one. And here, if I draw it, starts here and ends here. So actually, although it looks different, it's the same voltage. In other words, in this circuit, putting the voltmeter around the battery gives the same result as putting the voltmeter around the variable resistor. For your vocabulary, this is called the terminal voltage. So if I said the terminal voltage is, I mean this, which in fact is the same as this anyways. Okay, can you note that please? Yes, question? What does?
That's free.
Yeah, but I thought by drawing my little pictures slowly, you could see that this, by placing this here or here, it's equivalent of getting the voltage potential difference here. Although it looks like I'm measuring across the battery here, I'm actually still measuring across this. Yeah, that's the point I'm making here. It looks as if I'm measuring something different in the pictures. In fact, I'm measuring the same thing. In both cases, I'm measuring the potential difference here. That's called terminal voltage. Can you write that word down, terminal voltage?
Teacher,
Yes.
for the last one, V versus I,
Yeah.
isn't it like this? Cause
Did I
V,
not draw it like that?
Yeah, because V equals to negative RI plus V.
One is going up and the other is going down.
But E equals to V plus IR, so IR over there.
Huh? Hang on, slow down. Which one am I looking at first? The first one I did or the second one?
The second one.
Okay, this one here.
Yeah.
What's the problem?
Minus R.
Minus or. Minus or. Minus or.
Yeah, so the slope should be like this.
Oh, so sorry. So sorry. V is EMF. Huh?
Number 2.
Here? Yeah, but you're saying this is wrong. Right, hang on, let me fix it.
No, the below one is wrong. Yeah.
1, 2, 3, 4.
No, it's the one.
5.
The black, yeah.
5 is wrong. Okay, fine, let me fix it. V equals EMF. I have my signs backwards.
Yeah.
Thank you. That's a minus, that's a plus. So of course, then that changes this. So sorry. So this is going down. So here the OR is minus M. Thank you. If you can fix that, please. But that feels wrong. Makes me feel dirty. If I swap the I and the V, the graph is always going down.
I don't know.
Feels so dirty. Something in my heart says this is wrong, but I can see it's right. So, okay, did you fix that? Yeah. Yes. Oh yeah, back down to that. Can I scroll down?
Oh.
Yeah. Okay. Terminal voltage. Continue? Yes? Okay. Let's have a look back at the question. So, here's an example, something that you might get in the exam. You have your potential difference on your voltmeter, and you have your current on your ammeter, and question 1 is to graph this. Now, you have a choice. You can put the I here and the V here, or you can put the V here and the I here. There's nothing in the question that actually says which one you have to do. Although, I suppose, I did say in the title here, it's potential difference against current. So, that kind of tells me this one should be potential difference and this one should be current. Although, like I said, you can have it either way around you want. We just have to remember what the slope is. So if I go this way, VI, or if I go this way, IV. In this case, the slope, the OR will equal, we said, minus IV. Okay. In this case, the slope is minus M, and in this case here, the internal resistance is minus 1 over M. I will do this graph. Please read the question carefully in the exam to see if it's a clue for which one they want. But I'll do this one here. So just to write down the formula again, EMF equals V plus I or. So V, which is on the Y, equals minus or I plus E. So that is M X plus C. Now, one advantage of this formula is that this value here has a meaning. What's this value here? This is the EMF, isn't it? So that's actually an advantage with this formula. Okay, so can you write down these values and then we'll make the graph? What? Did you write this table down, Jerry? Oh, so lazy.
Intelligence.
Intelligence or laziness?
Intelligence is for lazy people.
I think laziness. Okay. Got that? Yeah? Continue? Okay. Let's have a look here. No, I need to open up my graphing program. Office. Calc. Okay, I'm going to graph this and you're going to graph it too. So while my program's loading, why don't you get a start on making the graph and I'll make the graph too. So remember we said we're going to put the V here and the I here. If you can start making that graph, please. So you need to go from 0 to 1 and 0 to 2.
Do you need graph paper for this yet?
Oh my goodness, yes.
I need to receive to prepare one.
Oh no. No. Graph paper will be provided. Okay, let's have a look now. So potential, this is current in amps first and then potential difference in volts. And the current goes from 1 to 0.1, correct? And then the voltage, what does that do? It goes from 1 to 1.9, and it increases in 0.1s. Okay, let's make the graph. Insert chart. What type of chart? No, you keep saying line. It's actually scatter. Scatter. Okay, title is voltage against current Wait, now I'm confused. 1 or 2 hours in current? 2 hours. X is current in amps, and Y is voltage in volts. Okay, let's see what this looks like. Okay, nice. Oh, forgot to put in the vertical lines. Doesn't matter. There we go. And we shrink this a little bit. There, perfect. Well, I'm missing the vertical lines. Right, so what's my first question? Make the graph. B, what's the internal resistance? Okay, so we need the slope here. Because if I look back here, we said the R is minus M. So for part B, the R will equal, let's see, what's that distance there? That's 1.9, isn't it? No, what am I saying? That's is that 0.9? That distance? 0.9? No, from the top to here.
Yes.
0.9? So it's 0.9 over 0.9 over 0.9? Yeah, okay. Great. So the internal resistance is 1 ohm. Yeah, well I had 2 minuses, so just made it a plus. It's minus because it's going down, and it's minus because it's in the formula as a minus. So there's actually a minus here. And C, what's the EMF? So if we look back here, the EMF is the C. So if I look at my graph, if you continue this up, would this hit 2? 2.2? Hang on, there's an easy way. I can get the exact value from finding out the equation. 2. Minus 1 is the slope and 2 is the intercept. So the EMF is 2 volts. Yeah, are we happy with that? Now, I have another example to do. One more. Can I do the other example? Scroll down. Okay. Thank you. Now, we've used this formula, EMF equals V plus IR. Yep. But we haven't used this formula. What's the other one? Yeah, I R plus R. Yeah, we haven't used that one yet. So if you look at this one, again, it's going to be the same type of problem. We don't know this, and we don't know this, but maybe I give you these, for example. So if there's 2 things in this we don't know, then how many equations will we need to have? 2. We'll need to have 2, which means I need to tell you 2 parts, 2 pieces of information here. So what will happen here for these types of problems is, I'll say there's some battery, but you don't know the EMF, and you don't know the R. And then this passes through a resistor, and I'll give you this resistor, and I'll give you this current here. So I'll give you the or and I'll give you the I. And then what I'll do is I'll change this. I'll put in a bigger or. And then of course the current will change. Alright, so in the first case we'll say when or equals this, the I will equal something, and when we make, let's just go with something simple, let's just go with 2 ohms, and then we'll make the or bigger here, we'll make it 3 ohms. The I is, I don't know, we'll say 500 milliamps, and then the I here. Now let me pick reasonable numbers in my head.
400.
Dude, just give me a few seconds to think, please. Thank you. You just can't resist, can you? I'm going to pick my own number now. I'm going to pick. Leave me alone. I'm not going to pick any of those numbers. I'm going to pick 250. There, I'll show you. 250 milliamps. Okay? I'll give you a minute. You have enough information to work out the EMF and the internal resistance. Because remember, these here, they don't change. These are constants. It's only this and this that can change. Okay, I'll give you a minute. Tell me what the EMF and the OR is. Okay, go ahead. Look at that. Lewis times.
It's program yourself.
Yes.
How?
Magic. What's Lewis time? Time for the Lewis. Because I made up the numbers, and maybe I made up bad numbers. Did you get a minus number? Did you get a minus number?
Equal minus 1.
Is it because the I is too small?
No, the current is too small.
That's the I.
Oh, sorry, wait, stop! Is that still too small? Alright, no, I'm not going to do that. I'm going to go with it. Sorry guys, this I is a bad I. What's so great about 333?
Now we equal.
No. 400, sorry, we'll make it 400. Okay, let's have a look. Well, we'll do it together. Okay, so firstly we can say E equals I, which is 0.5, or which is 2, plus or. And secondly, we can say E equals, what's this one here, 0.4, 3, plus or. Now this is actually easy to solve because we can say here 0.5 times 2 plus or equals 0.4 times 3 plus or. So I get 1 plus a half or equals whatever.
1.2.
Thank you, 1.2 plus 2/5 or. Yeah? 0.5 minus 1/10 or equals 0.2. So the internal resistance is 2 ohms. Yeah. You sound so surprised. Okay, you have that? Alright. So what you can do, Yeah, you can take a break for a couple of minutes and then we'll start the next lesson. I have the worksheet, I'll give it to you later for this one. The next what? I just closed it now. I'll tell you when the next bus is if you want. I'll tell you when the next bus is. I also have the train times on it too. It's amazing.
It's like you're developing doctor.
Yeah, I know. That's more interesting.